when we name covalent molecules, and these are molecules that are all comprised of nothing but covalent bonds, we should note that there are a couple of conventions that we have to abide by. All right. So first, let's just draw this out. And the first thing we're going to draw out, this is neon. Okay. Neon gas. Now, neon itself, it's a covalent structure. It's a non-metal. But there's no covalent bonds associated with neon. It's a monoatomic gas. Okay, so this is a monoatomic gas. All right, not a molecule. Because in order to be a molecule, there has to be more than one element bound to it. Okay. When I go to H2, which is the elemental form of hydrogen gas, this is a molecular gas, or a molecule. But because it's hydrogen, we can call it an elemental molecule. Funny story, hydrogen didn't used to be called hydrogen, it was actually called phlogiston for a long time. Because people noticed they could generate phlogiston and then it would burst into flames. They didn't really understand what exactly was going on, but they knew it was cool. So they called it phlogiston because it's pretty awesome. All right. When I go to H2O, all right, at this point, what I'm going to is a compound. Right? But to say, because of the nature of the compound, because it's covalent, we simply call this a molecule. So this is just a molecule in general. I'm going to put in parentheses here that this is also a compound because it has more than one element bound to it. Okay? But a molecule generally indicates that you're going to have a lot of a lot of covalent bonds in between these things. Okay? To give you some background and some history that's associated with these, when they were discovering the differences between molecules, they noticed that some covalent structures can form bonds, multiple compounds with different atoms. All right. So to give you an example, one thing that we're all familiar with is carbon dioxide. It's a gas, right? But we also know that there's also carbon monoxide, which is also a gas as well, both of which are generated when we burn fuel in our cars. The catalytic converter that's in a vehicle is used to generate or turn carbon monoxide into carbon dioxide. Okay? There's other oxides as well, right? You can do SO, a gas, or commonly SO2, which is a gas, or SO3. All of these are gases, right? And each one is a sulfur with an oxygen bound to it. One has one oxygen, one has two, one has three. Okay? Now, to give you some history associated with it, I'm just going to underline these ones. Proust was a chemist who identified that anytime he separated carbon dioxide into its base elements, carbon and oxygen, he always came up with the same proportion of it. Okay? And Proust came up with this thing called the law of definite proportions. And all that meant is that every time he separated carbon dioxide into its component parts, he always noticed that he got 1 part carbon and 2 parts oxygen based upon the mass, the known mass of those elements. So what he did is he always noticed that if you burn, say, let's see, well, I've got an example here. If he burns, say, 36 or 50.5 grams of carbon dioxide, he would get a value, and he was able to predict this. He was able to predict that the value he would get of the oxygen was 36.7 grams, and that the amount of carbon that he'd end up getting is 13.8. Okay? And the ratio that he was able to get, and I forgot to put the fraction on here, was 2.66. Right? And this indicates that oxygen is a little bit heavier than the carbon. But he was able to look at this and say, anytime he was able to break down carbon dioxide, regardless of the mass that he used, he was always going to get something that was a 1 ratio of carbon to 2.66 ratios of oxygen associated with it. All right? Dalton, who is also a good chemist, worked with carbon dioxide and carbon monoxide. And he worked off of Proust's idea that you could have definite proportions of carbon and oxygen associated with it. And what Dalton did is that Dalton took the mass of ratio of oxygen to carbon and carbon dioxide, the mass ratio of oxygen to carbon and carbon monoxide, and he noticed that there was always a proportion that's associated with it. And this is the law of multiple proportions. Using Proust's own work, what he did is he looked at carbon monoxide. And he noticed that carbon monoxide, the ratio was 1.33 to 1. Okay? So it was 1 to 1.33 carbon to oxygen as far as mass goes. Okay? And what Dalton then said is this, okay, well, I'll combine these two together. If I look at the 1 to 2.66 ratio of carbon dioxide to carbon monoxide, okay, what he was always able to get out of this at this point was a 1 to 2 ratio of carbon to oxygen. And what this means is that on the top, I've got 2 to 1 here. So 1 to 2 to 1 to 1 ratio, okay, with this particular fraction, which meant that the carbon dioxide had two oxygens, and the carbon monoxide only had 1 oxygen. All right? And what he was able to do, what this proved, and this is a little bit of history lesson, what this proved is that you can have molecules, or covalently bound materials, and these molecules do not always have to have the same number of oxygens or the same number of other things that are bound to them. Okay? But you did note that there's always a ratio of how these things worked out. Okay? So if I look at the sulfur dioxide, okay, if I looked at SO2 and compared that to SO3, okay, if I use the law of multiple proportions, what I would note is that I would have a 1 to 2 ratio up on top and a 1 to 3 ratio on the bottom. And this is just something that was done. And it kind of amazes me that they were able to do this way back in the 18th century when they didn't have a nice fancy lab in order to do these types of experiments. So they're able to prove these laws and, beginnings of scientific enlightenment at this point. All right, when we talk about naming covalent molecules, we should be aware that when we're naming these things, there's some things that we have to take into account. And when we name these things, and we're drawing out their formulas, things may be a little bit different. So let me put it this way. All right, so I'm going to put this into groups of formula. All right, and the first one, okay, is going to be a structural just write down the molecular formula of something. And the molecular formula indicates what's inside any sort of structure. Okay? So if I look at the molecular formula of, say, methane, methane's molecular formula is CH4. Okay? I've got one carbon and 4 hydrogens. Okay? If I look at the molecular formula of ethanol, I've got 2 carbons, I've got 6 hydrogens, and I've got an oxygen associated with it. And generally when we name things that are carbon-based, carbons and hydrogens come first, and then all other elements come along in their order, okay? So if I was to come up with this compound, let's say I had C4H7, I would go BrCl IO, excuse me. Right? We do these all alphabetically in the molecular formula. All right? When I go to structural formula, This gives me a little bit more information as to where everything shows up in a molecule. All right? Methane structural formula is going to be the same as the molecular formula, CH4. Okay? And what this means is that carbon is the central atom and the hydrogens are all bound around it. The reason being is that hydrogen is always going to be a terminus, and as a result, it has a lower priority on the structural formula. When I go to ethanol, however, I now write this as CH3CH2OH. And this gives me more information, because what this means is that this carbon is bound to this carbon, which is then bound to this oxygen. And then each one of these carbons, this one has 3 hydrogens, this one has 2 hydrogens on it, and that one has 1 hydrogen on it. All right, if I take this formula and I write this out in a structural formula, I can write it out this way. I can write, let's see, HOCH2 CHI CCl, or let me put it this way, CBrCl, okay, and then CH3. And what this says is that I've got all these carbons are connected to each other. So I put this in kind of a line diagram. Let me condense this. So OH, CH2, CHI, CBrCl, CH3. And what this structural formula states is that this oxygen is connected to this CH3. Okay, this carbon is connected to that carbon. This carbon has a hydrogen and an iodine attached to it, but each one of these can only make one bond, so we treat them as terminuses like the hydrogen. Okay, so this carbon is connected to that carbon, this one is connected to that carbon. Okay, and the Br and Cl are attached to what precedes it. So, if we look at it this way, these hydrogens are connected to that carbon, that hydrogen and this iodine are connected to that carbon, this Cl and this Br are attached to that bromine, okay? These hydrogens are attached to that carbon, right? And this hydrogen and oxygen are connected that way, okay? Those are structural formulas. And there's one more thing that we use, and that's something that we call an empirical formula. And the empirical formula, unfortunately, doesn't give us as much information. But what it does do is that it drops particular groups into a similar state. All right? So if I look at, say, C2H6, the empirical formula drops this down to the least common denominators associated with this thing. So the empirical formula for C2H6, which is ethane, becomes CH3. That's the empirical formula. It's the lowest common denominator of this particular structure. If I look at the empirical formula of, say, let's do cyclohexanol, so C6H12O, okay, there's cyclohexanol. The empirical formula of this is going to be C6H12O. The reason being is I can't divide that oxygen any further. It's got to remain that. If I was to change this to glucose, C6H12O6, what is the empirical formula of that? CH2O. All right? The reason that empirical formulas are used, you're going to look at them going, well, that's kind of pointless. Why are we doing that? Empirical formulas are actually important whenever we do elemental analysis of something. Because what the empirical formula tells us is what the ratio of each one of these things is going to be if I blow this stuff up and measure the mass associated with each of these things. Okay, so that means that the ratio here, what I get as far as ratios go when I do the law of definite proportions or multiple proportions is going to be 1 to 2 to 1. Okay? All right.